Okay, let's implement CNN together. This CNN is similar to what we've implemented in previous sessions, like image classifiers. Before we get into implementing DeepConvNet, let's talk about the input size. We are going to talk about Cypher10, which has the image size of 1 by 28 by 28. And network architecture, the picture looks like this. First, convolution layer, and then ReLU, another convolution, and then ReLU, and then pooling. We're going to repeat this process 3 times. And after that, we're going to connect a affine layer, which is fully connected layer. And then ReLU follows, and we can apply norm. Norm can be either batch norm or group norm, instance norm, any norm, or dropout. Another affine layer, and then norm, and then softmax. Okay, this is the architecture. And we're going to implement multiple methods. The first one is, of course, initialization. And the second one is going to be predict method. It receives an instance or instances, and it also needs to receive train flag because normalization layers have different behaviors, whether they are in chain operation or test operation. In 2 cases, the behavior of normalization differs. Therefore, we need to pass train flag as a parameter to this method. And we're going to also implement loss. Here, X is the instances, and T is the ground truth labels. And we are going to implement accuracy as well. And here, we're going to pass the batch size as a parameter. And we are going to also implement gradient because we need to be able to train this network. And for this network, we're going to implement 2 additional methods. The first one is save parameters because it's going to take quite a lot of time. And after training this network, we might want to save the weights. And after that, we might reload the parameters, weights, and they use in other cases. Here, we are going to use Pickle library to store the weights. And when we have save operation, we need to be able to load the saved parameters. So we are going to implement load params method like this. Okay, first things first, we're going to implement the initializer first. Initializer is going to receive the input dimension, which is 1 by 28 by 28. And we're going to pass convolution parameters as a dictionary. We need to specify the number of filters like this and filter size like this, and the padding and stride like this. And because we are going to have 6 convolutions like this, we need to define 6 conv parameters. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And after each pooling here, we're going to increase the number of filters, double the number of filters, as in ResNet. And we're going to fix the filter size over the network. And here we're going to use the path size of 2. Think about the reason why we need to use 2 here. And we also need to specify the hidden size and the output size. Because the dataset Cypher10 contains 10 classes, we need to output 10 scores. Okay, so this is the parameters for the initializer. And what we need to do next is weight initialization. And to do so, we need to calculate the number of nodes in each layer. Why do we need to do this? Because we need to determine the scales. We learned in the previous sessions that when we initialize the weight values through a square root of 2 divided by the pre-node nums, then it's going to give us quite well-distributed gradient flow. And 2 for ReLU, and 1 for 10H. This is He initialization, and this one is for Xavier initialization. Just to achieve this goal, we're going to calculate the number of nodes. Actually, these numbers specify how many connections to the previous layer are there for each neuron. This is what these numbers mean. For the first layer, there are 1 times, 3 times, 3 times connections between the first and second layers. And 16 times 3 times 3, 60 times 3 times 3, 30 times 3 times 3, 64 times 3 times 3, and 64 times 4 times 4, and hidden size. If you are not certain or confident why these numbers are like this, think about it on your own. With these numbers, like padding, filter size, filter num, and pooling layers here. Okay, think about it on your own. All right, this is the weight initialization scales. And then we're going to define the parameters as a dictionary. When we define the parameters, we need to keep track of the pre-channel num. Because when we define convolution, we need to specify the number of channels of the previous layer and the current layer. That is why we are keeping track of the previous channel num here. Like this. And because when we implemented the conv layer, the conv layer does not receive the number of filters or the size of pad or stride. It also receives those parameters. However, we need to specifically define the parameters and pass the parameter to the convolution layer. That's why we are defining parameters here. plus str dx plus 1 like this. And here we're going to use this weight init scales and np random rand n, and we need to pass filter number for channel number and come with parameters, filter size, conf parameter, filter size, like this. Okay. There shouldn't be bracket here. Okay. And I guess this should be, there should be 2 parentheses like this. Right. And we also need to define the bias like this. And this is going to be an array of zeros. This is simply the number of filters. And we update the pre-channel num as the current filter number. And we also need to define the parameters for fully connected layers. Here we're going to use the init scales as well. Okay, and self params, P7, and P0s, even size, this. We also need to do this for the 8th weight, like this. It's going to be output size, scale 7, even size n, output size. Although we are doing these implementations manually, this is done automatically when we use frameworks like PyTorch and TensorFlow. So don't worry too much about this. And we need to create layers from now on. So first, define a list like this. And we initialize the convolution layer like this by passing the parameter matrix like this. And we also need to pass size of stride and path. And we need to do this for W2, 3, 4, 5, 6. E2, 3, 4, 5, 6, like this. 2, 3, 4, 5, 6. And here, our architecture looks like this. After the convolution layer, a ReLU follows, and then another convolution and ReLU. So we are going to put ReLU between each convolution ReLU like this. ReLU, 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 ReLU. And after convolution, we need to put on another ReLU. And after 2 convolutions, we are going to add normalization layers. Here, even though we haven't talked about pooling specifically, let's just assume that there's a pooling layer like this for height, for width, and stride 2. Okay, we're going to add pooling layer after 2 convolutions. So 2 convolution, ReLU, pooling, convolution, and pooling. Then we're going to add affine layers. Affine layers are just fully connected layers. We're going to pass the weight like this, bias like this, and we defined 2 fully connected layers. And between affine layers, there is a ReLU, and after ReLU, we should put a normalization layer. Here, we're going to just use dropout. And after affine, we add another dropout. And the last layer is going to be softmax with loss. This is the initial implementation of the initializer. It looks quite complicated, however, when you look at closely, this is nothing but just defining these building blocks and then connecting those layers, blocks. Okay. And how do we do prediction? It's pretty simple. When we receive the input, what we are going to do is like this. For each layer, in the layer set or layer list, if this is the instance of normalization, like dropout, we need to pass the train flag, because the behavior of normalization varies depending on the current mode. If it is train mode, then it should calculate the running mean. If it is not, if it is not in the training mode, like test mode, then it does not calculate the running mean. So we need to specify train flag. Otherwise, we just pass the input like this. And after passing through all the layers, we just return the result like this. Calculating loss is quite simple. You just predict the results by passing the train flag. However, when we calculate the loss, it is usually the train mode. So we just pass train flag is true. And we return by passing this result to the last layer, which is softmax with loss, like this. And calculating accuracy is not that difficult. If the dimension is not 1, then T, we just get the ground truth labels. And because we need to process this input with batch, we divide the total number of items with the batch size, like this. And we get the sample, ith batch to i+1 batch. And we also retrieve the ground truth label. And we perform prediction like this. And when we're calculating the accuracy, we are not training or modifying the weights. So the flag should be false. And to accuracy, we add the number of correct labels. And the return accuracy divided by the number of instances. And to calculate gradients, we need to perform forward operation first. That is going to be calculating loss. And we also need to go through backward. And the first upstream loss is 1. And we pass through the last layer. And we copy the layers. And what we are going to do is reverse the order. Because when we calculate the gradient, we need to start from the back and come to the front. That's why we are reversing the layers. And for each layer in temp layers, we calculate the gradients, local gradients. We pass gradients using backward. And to retrieve grads, however, we need to care about fully connected layers and convolution layers because pooling does not have any parameters trainable. So we're only considering convolution and fully connected layers. Here, fully connected layers are affine layers. And from each layer, we retrieve the gradients like this. Yeah, like this. And we just return grads. Other components don't have any parameters trainable. So we only care about convolution and fully connected layers, which is affine layers. All right, after a long period of training, we want to save parameters. And to do so, we're going to define another dictionary like this. And PyTorch also uses dictionary to save parameters. Key and value and self params, items. What we're going to do is store each key and value pairs in this dictionary. And after we are done, we open a file specified as the file name and write byte mode and call pickle dump. And it will store parameters as this file name. This is pretty simple. And after we save, we need to be able to load the saved parameters. And to do so, we do simple open file name, and the mode is read byte. You just call this pickle load method. And for each value, key and value in these items, we store these values. And for each layer of convolution and fully connected layers, we put the parameters we ruled like this. Okay. Okay, this is the implementation of a simple deep convolution neural network. And because we have gradient method and save params and load params, it is quite easy to write a code for training this the convolution neural network. And you can do this on your own by referring to previous sessions.